Analysis of annual NTSB accident reports reveals a consistent, lethal trend. Weather-related incidents account for a disproportionate share of general aviation fatalities. These tragic accidents represent mechanical failures of a completely different sort, a breakdown in the pilot's understanding of atmospheric thermodynamics. Today, we are stripping the atmosphere down to its first principles to help you upgrade your pre-flight decision-making process. If a single physical concept in this breakdown changes your next flight plan, please click the like button. For those of you looking for rigorous, professional-grade aviation deep dives every week, hit subscribe. Approaching the sky as a strict mathematical system provides a reliable framework for flight safety that intuition alone cannot match. Significant aviation weather is confined within the troposphere, a layer of air that ends at an average altitude of 36,000 feet. The standard lapse rate defines the thermal behavior here. For every 1,000 feet of altitude gained, the temperature drops exactly 2 degrees Celsius. This predictable cooling rate serves as the engine for every weather hazard a VFR pilot encounters. When the atmosphere adheres to this uniform cooling pattern, it remains stable, resulting in smooth, manageable flying conditions. Deviations from this standard math create the unpredictability that leads to hazardous flight environments. Calculating the lapse rate allows a pilot to identify the specific altitude where invisible moisture will condense into a visible physical threat. In a stable atmosphere, any air parcel displaced upward naturally sinks and returns to its original level. This stability forces air to spread horizontally, creating stratus clouds, steady precipitation, and smooth air, though it often results in poor visibility. An unstable atmosphere occurs when that displaced air teets rising, expanding, and accelerating as it moves higher. This upward momentum leads to rapid cumulus development, severe turbulence, and violent weather changes. A temperature inversion reverses the standard lapse rate. Here, the temperature increases with altitude, creating a dense, stable layer that acts as a lid. These inversions trap fog and pollutants near the surface and generate dangerous low-level wind shear right at the boundary of the temperature shift. Stable air and inversion caps often hide deteriorating visibility and shear zones behind the appearance of a calm, clear sky. Weather systems scale up when contrasting air masses collide to form fronts. A warm front occurs when advancing warm air slides over a colder mass. This creates a shallow slope that can extend for hundreds of miles. This progression provides a visual timeline. High cirrus clouds transition to cirrostratus, then altostratus, and finally, thick nimbostratus rain clouds. This mechanical structure causes a slow, broad deterioration of flight conditions across entire regions. In contrast, a cold front features a steep slope. Dense, cold air bulldozes under the warm air, forcing it to rise violently and rapidly. The result is a narrow band of cumulonimbus clouds and intense, rapid weather, followed by a sudden return to clear skies. Identifying the type of front ahead tells you the exact shape of your weather window, a long, creeping decline or a fast-moving, violent wall.
Consider a practical scenario. You are planning a 3-hour VFR flight. Your destination's weather forecast includes a 4-hour becoming window. The forecast shows TEMPO TSRA, meaning temporary thunderstorms and rain, at the exact time you plan to arrive. Tell us your reasoning for a go or no-go decision in the comments. The safest decision is to ground the aircraft. Flying into a forecast overlap with temporary thunderstorms is an unacceptable risk for VFR operations. These storms evolve in 3 distinct stages. The cumulus stage consists entirely of powerful updrafts as the storm builds its energy. The mature stage is the most dangerous. Here, the storm contains simultaneous updrafts and downdrafts, producing maximum turbulence and precipitation. Finally, in the dissipating stage, downdrafts dominate the cell and the storm's energy begins to exhaust itself. Pilots must maintain a minimum distance of 20 nautical miles from any severe thunderstorm cell.
Flying under the anvil is particularly hazardous. Severe hail can fall from the top of the cloud and strike an aircraft up to 20 miles ahead of the actual storm. These 20-mile hazard radii are absolute hard stops in your flight planning, not obstacles to be navigated through visually. Structural icing requires 2 simultaneous conditions: visible moisture and an aircraft surface temperature at or below 0 degrees Celsius. Rime ice forms in stratiform clouds. It freezes instantly on impact, appearing as a white, rough, and opaque layer. Clear ice forms in cumuliform clouds, or freezing rain. The water drops spread before freezing, creating a transparent, heavy, and very dense coating. Clear ice is the more serious threat, as its density and weight can rapidly compromise a wing's aerodynamic lift. Freezing rain stands as the most hazardous icing condition a pilot can encounter in the troposphere. You must use the lapse rate to identify the freezing level. Knowing where that altitude intersects visible moisture is the only way to avoid a terminal icing encounter. Mountain waves occur when strong winds cross a ridge and create massive standing waves on the leeward side of the terrain. Stationary, lens-shaped lenticular clouds serve as the primary visual warning of this intense wave activity. The rotor zone beneath these wave crests contains the most violent turbulence, capable of structural damage to light aircraft. At the surface, fog types are defined by their formation. Radiation fog occurs during overnight ground cooling under clear skies. Advection fog forms when warm, moist air moves over a cold surface. Unlike radiation fog, this type requires wind and often appears as sea fog. Steam fog develops when very cold air moves over much warmer water. While radiation fog clears as the sun heats the surface, advection fog can persist long after sunrise. Local topography acts as a force multiplier, turning standard atmospheric shifts into localized, lethal traps. We started with a deal. If you learned something new about icing, fronts, or thunderstorm mechanics, please hit the like button. Between thunderstorms, structural icing, and zero visibility fog, which of these hazards do you find the most difficult to plan for? Surviving VFR flight requires outthinking the laws of physics before the engine ever starts.